Today we're going to continue our discussion on vibrational spectroscopy. In the previous lecture, we discussed the selection rule for vibrational spectroscopy and talked about the Morse potential, the harmonic oscillator, and this anharmonic Morse potential, and how that sort of affects the vibrational energy levels and transitions you would expect. So today we're going to expand on some of that. Go back and watch the previous lecture if you're a little bit lost. But today we'll expand on that and cover really three parts of interpreting and understanding vibrational spectra. So that's what we'll talk about today, vibrational spectra. The first point we're going to talk about with regard to vibrational spectroscopy and thinking about the spectra we expect for a given molecule is to think back briefly about where vibrational peaks come from. So where do the spectral peaks originate from? Where do they come from? And so if we think about this Morse potential that we've drawn a couple times in the previous videos, right? Something like this, where it's energy versus function of bond distance. You can call this R, you can call it whatever you want, and this is energy here. And here's our Morse potential, right? You know within this electronic structure that has its own term symbol, something like sigma 1g sigma plus, there's various vibrational levels, okay? And I'll draw these kind of far apart because I want to illustrate something. And this would be, the first vibrational level, n equals 0, and this would be the second vibrational level, the excited vibrational state, n equals 1, right? And for a diatomic, there's only one vibrational frequency, but there's different vibrational amplitudes here, which is what the quantum number is telling us. Now, the selection rule we discussed last time is delta n plus or minus 1. Okay, we derived that in the previous lecture in terms of vibrational spectroscopy. Now, the other good thing about vibrational spectroscopy, in terms of limiting the number of transitions you expect, is that for most things, while most experiments are done at room temperature, 300 Kelvin, and for most molecules, only the lowest vibrational state is really going to be populated at 300 Kelvin. So although you have this excited vibrational state, really most of the molecules live down here. And so the only real strictly vibrational transition you would expect, and these differences in energy here are about IR wavelengths. So in this IR spectroscopy, the only transition you expect would be this transition, right? From the ground state to the excited state. And so if you were imagining a spectrum that you were taking, right, where the spectrum is the intensity of some peak as a function of wavelength or frequency, maybe we'll think about frequency here, then for this species, you would only expect one peak, right? And one line in your spectrum, the intensity of which has something to do with, the photoabsorption cross-section of that molecule, right? If this is an atom, there are no vibrations. This doesn't matter. But in molecules, there's vibrations, and if we're doing IR spectroscopy, our IR spectrum, we'd expect to look something like this. However, the first point we want to make today, where do these spectral peaks come from, is that it doesn't look like this, okay? And you could say, okay, well, maybe it's a wider peak because there's some experimental, error and resolution limits, but that'd also be wrong, okay? Truly, the peaks you get, even for this one vibrational transition, might look something like this. Right? 5 peaks, maybe 10 peaks, it depends. But where are all these peaks coming from? And where these peaks are coming from are the fact that even though all the molecules are down here in the ground vibrational state, we know there's other types of energy. And in fact, there's rotational states here for this ground vibrational state. And maybe there's 3 there for that one, and maybe there's 3 here for this one. Although there's more, I'm just drawing 3. And so when this molecule transitions from the ground vibrational state, it may not only be in the ground rotational state. Okay? So it's not only this transition that could happen. In fact, that doesn't happen for diatomics because you need a change in J, as we'll see in future lectures. But you would expect multiple peaks. Why? Because multiple rotational levels are populated. And so you can draw all the arrows here where the change in rotational state is plus or minus 1 within this vibrational state of plus or minus 1. So even in a diatomic, where you expect there to be one vibrational frequency, because there's 2 atoms, and the rule is 3n minus 5 vibrations for linear molecules, and a diatomic is always linear. So n is 2, there's 2 atoms, 3n minus 5 would be 6 minus 5, 1 vibration. Even for that 1 vibrational frequency, you wouldn't expect just 1 peak in the spectrum, even though just the ground quantum state of that single vibration is populated. You get multiple peaks because of this rotational splitting. Okay? So the peaks come from what's called rovibrational transitions. Okay, so within vibrations, even a single vibrational transition, you're going to have several different rotational possibilities, which means different energies. Okay, so that's the first point. When we're thinking about IR spectroscopy and how many peaks we expect, there's going to be a lot of peaks, even in the case that it's room temperature, only the ground state's populated of the vibration. Right? We can only access the n equals 1 state. We're still going to be able to access a whole bunch of different peaks and get a whole bunch of peaks here, even for that single vibrational transition. Okay, so that's point number 1 when thinking about vibrational spectra. Point number 2 is, let's expand on this a little bit and think about, okay, how many groups of peaks do we expect? If the case can be made, which we did on the previous slide, that we're going to have, a group of peaks, not just a single peak, for this one vibrational transition, let's think about how many of these groups we expect, which is to say, how many sort of vibrational transitions do we expect, which we know will contain multiple rotational transitions. And let's think again about our molecule. So in a diatomic or anything linear, it's 3n minus 5 for linear, and this is a degrees of freedom argument where you're removing the translational and rotational degrees of freedom from the total degrees of freedom, 3 times the number of atoms. 3n minus 6 for nonlinear, removing 3 rotations and 3 translations. So let's think about a molecule like methane, CH4. There are 5 atoms. It is nonlinear. So 15 minus 6 equals 9. There should be 9 vibrations. And if this methane is being investigated at room temperature, we expect they can each undergo n equals 0 to n equals 1 transitions. Yes, there could be greater transitions, which we talked about last lecture as overtones, but for now we're sort of limiting this to not overtones, just these allowed vibrational selection rule processes. Okay, so how many groups of peaks do we expect? We might expect for methane 9 vibrations, each of which should have this rovibrational splitting, because they each can undergo n equals 0 to n equals 1 transitions. But of course, there's going to be different rotational levels populated for that ground state. However, right, the answer here is not 9. Okay? And the answer is not 9 here because multiple vibrations, maybe I'll write this down here, multiple vibrations can have the same energy. And remember, the peaks where they are in a spectrum is proportional to frequency or the energy. So if these vibrations themselves, multiple vibrations have the same exact energy, then the transitions are going to be the same, and they're going to be at the exact same place in the IR spectrum. Okay, so let's actually look at this in practice and look at our molecule of methane, right? Keeping in mind here that multiple vibrations can have the same energy. So I took the liberty to run methane in Gaussian, a quantum chemistry program that solves the Schrödinger equation for all these atomic coordinates, optimizes the geometry, solves for the molecular orbitals, analyzes the energy. It's a really fabulous program. Out of it, you can get a whole host of information, one of which is the vibrations. So let's look at the vibrations, and this might be hard to read in terms of the numbers. It's not that important. But what it tells you here is each of the types of vibrations that it can have, and it tells you the frequency. And so, as I said before, multiple vibrations might have the same energy or might have the same frequency. And the real reason is molecular symmetry, okay? There can be these types of motions of molecules in a symmetric molecule like this. I should say a symmetric movement of atoms in a very symmetric molecule like this that correspond to different vibrations, but all with the same energy. So let's take a look at this. And the beautiful thing about Gaussian is you can also play little animations, right? So here's a dancing vibrational mode. You can even speed it up or slow it down if you want to sync this to music. It's pretty fun. But there's one vibration, okay? And another vibration with the same frequency is this. And another one with the same frequency is this. So here, they certainly look like distinct vibrations, but the overall net movement of the atoms and movement of the electrons is identical. So all three of these have the same vibrational frequency, but they're independent modes of vibration. And so three of those all have the same energy, and I would expect one set of peaks in my IR spectrum for all three of these modes, because they're going to correspond to the same energy. We can look at some other vibrations. Here's another group of three, all with the same energy. So you can see these two especially, it's quite obvious that these are similar types of motion and have similar energies. But this one also has the same energy. So you probably can't read the energies here, it's a little small, but these last three vibrations have the same energy as well. And so if I come over here and think about, okay, well, I have those for methane, two groups of triply degenerate, we could call them, vibrations. So instead of 9, right, we have vibration 1, 2, and 3, which all have a vibration and energy. We have vibrations 7, 8, and 9, which all have a vibration. And then we have vibrations 3, 4, and 5, which aren't degenerate. So already we've reduced the number of peaks from 9 to 5, right? Because 4 of those are going to be equally represented in 2 peaks. Okay, so that's the 2 groups of degenerate vibrations. Okay, so what about these other 3? Okay, and that's the third point I want to get to, is that even after we remove these symmetry degenerate vibrations, there's still other vibrations because not all vibrations are IR active. Right? The answer is no. Are all vibrations IR active? No. And we discussed this last time based on the selection rules of that these vibrations have to produce a net dynamic dipole. Okay? Not a permanent dipole, but this dynamic dipole that's more about the sloshiness of, say, the middle atom's electrons. And so some of these vibrations are not IR active. So we can go back to here. Okay, we can go back and look again at our vibrations, right? These three are degenerate. We expect one peak in our IR spectrum for those three because they all three have the same energy. These three are energetically redundant. We expect one peak or one set of rotational peaks for each of these three. But then you have these other three in the middle, okay? This one and this one. These two are degenerate in energy, but notice there's no net movement of the central atom. Okay, so a dead giveaway here is that when there's no net change in the center of mass, like there is no net change of center of mass with the motion of these atoms or the motion of these atoms, and I can rotate around and you can look at these two. They're similar types of motion. They're energetically degenerate, but there's no net movement of the central carbon atom. And so there will be no net movement on a basis of time of the electron density around this carbon, meaning it has no dynamic dipole. It cannot interact with IR light. Okay, this one, which is singly degenerate, also has no net dynamic dipole. And so these 3, 4, 5, and 6 here, which I was counting off as 3, 4, and 5, none of these have dynamic dipoles. So there must be a net change in the center of mass. During a vibration to produce a dynamic dipole. Okay, so there's some types of vibrations in carbon dioxide that have no change in center of mass, meaning those vibrations are not IR active. Okay, and those don't play a role in terms of CO2's greenhouse gas effect. But there are other vibrations of CO2 that do have a net change in center of mass, that do produce a dynamic dipole, that are responsible for the absorption of IR light in our atmosphere. And so the more CO2 we add, the more of that particular vibration we are exciting with IR light given off by Earth and trapping that energy in our atmosphere, leading to the rise of our global temperature. Same thing for methane here. There's types of vibrations that we were looking at here, some of which have no net change in the dipole and the dynamic dipole, and so won't be IR active. And so we actually don't expect a peak for that. We don't expect a peak for that. We don't expect a peak for that, because none of those produce a net change in the center of mass. Okay. So if there's no dynamic dipole, which we called mu prime in our previous lecture, i.e. u prime equals 0, then our transition dipole moment that we talked about from state 0 to some excited state m, that will be 0, and there will be no interaction between the light and the molecule. Okay, so that's what it means to be not IR active. If it's IR active, it means it does have some change in the center of mass and produces a dynamic dipole. Okay, so this is going to be the case for 3 of methane's vibrations. Okay, so that's 3. We removed 4 others from degeneracies. So out of these 9, there should be only 2 of the 9 vibrations that show up in our IR spectrum. Okay, so how many groups of peaks do we expect? Well, we expect in some spectrum, where we're measuring the intensity of light that is absorbed or transmitted, whichever you want to plot, versus an energy or frequency, we would expect 2 peaks. But really, we expect these to be 2 groups of peaks because of the vibrational or row vibrational splitting that I talked about at the beginning. And so we can come back and look at this. And the nice thing about this program is that it also, we can stop the animation, it'll show you the spectrum. It'll plot these things. And look at what it plots. It only plots 2 peaks, only the ones that produce a dynamic dipole. Okay? And thus produce these IR active transitions. Now, it's of course showing this as a single peak, but you know better now this is just a theoretical thing, that this will probably be broken up into multiple rotational peaks within this vibrational peak to give us a row vibrational spectrum. And so we can take a look at what that might look like. Here. So here's the spectrum from methane. Okay, and there's 2 distinct huge groups of peaks. We predicted here from our theory that there should be a peak at 1340, and here's the group of peaks at 1340. We predicted a peak around 3100, and here's the peak around 3100. But of course, it's split into a whole bunch of peaks. And what governs the intensity of these peaks, and where they are in the shapes and the heights, and where they are energetically and how spaced apart they are, right? Why doesn't it look like this nice peak? Because it's split into rotations. The spacing of those rotations, the spacing of these arrows we talked about at the beginning of today's lecture, and the height of these peaks, we'll get into describing exactly why they have that shape, spacing, and intensity in the next lecture. So that'll do it for today's lecture. Up next, we'll dive into rotational spectroscopy, which tells us something about the splitting of these vibrational spectroscopy peaks. See you next time.